Hello, everyone. Thanks so much for joining us. Today, it's my pleasure to introduce John Hewitt. John is a third-year PhD student in computer science at Stanford University, advised by Chris Manning and Percy Leong. He works on understanding and improving how unsupervised neural networks learn and process human languages. He is supported by National Science Foundation Graduate Research Fellowship and is the recipient of an EMLP Runner-Up Best Paper Award. I'm really looking forward to John's talk, so please join me in welcoming John and enjoying his talk. Thank you.
Thank you very much. Hi, everyone. I'm very excited to be here. Very thankful to be here, so thanks for the invitation. And so the title of the talk, I hope sounds exciting, and if it sounds like too much, forgive me for the moment, and hopefully by 3/4 of the way through the talk, I'll have convinced you that it is that the results actually back up, in terms of theoretical results at least, kind of the maybe grandeur of the title. And if not, then I'd love to hear the argument. Why not? Okay, so looking forward to giving this talk. Let's jump in. First, thanks to my collaborators. So this work is joint with Michael Hahn, Surya Ganguly, Percy Leong, and Chris Manning. And I'm listing the departments here because this was a really fun collaboration that started when I talked to Surya Ganguly, who does some deep learning theory work. And about 1.5 years later, here we are. And so there's a paper at EMNLP that you can look up. There's a draft up on arXiv. And this talk will be solely about this EMNLP paper. Okay, so there's two main subjects of today's talk: recurrent neural networks and syntax. So maybe for this audience, I don't need to convince you too much. But there is hierarchical structure in language that is important for understanding how the meanings of smaller units within sentences combine to form the meanings of larger units. So understanding syntax, like this tree, for example, and its hierarchy is important for understanding language. Recurrent neural networks, we've been training for many years now to predict the next word in a sentence as a language model. And we have some evaluations that treat them as language models that try to understand something about whether they can kind of figure out bits about syntax. So here's an example where you have the chef who made the pizzas. And in English, right, we have verbs agreeing in number with their subjects. And you have this hierarchical relationship, subject-verb relationship. And a good language model, a good recurrent neural network language model should know that the word is more likely than the word are, right? Even though you've got this sort of linearly close plural noun here, pizzas, the agreement should be with the subject. And in practice, recurrent neural networks do actually quite well on these kinds of syntax-dependent language model predictions. So seemingly, they just see sort of positive examples of sentences and they can sort of make the right predictions, which suggests that they understand something about this fragment of a tree on the right. And there's also sort of what I'd call rough evidence in that when you generate from recurrent neural network language models, even in today's day of massive pre-trained transformers, right? Looking back, say at Andrej Karpathy's 2015 blog post, it's actually pretty cool, right? The kinds of things that a modestly sized RNN trained on a modest amount of data can generate. Topically, it makes no sense. But syntactically, like here, there's this example of LaTeX code that like almost compiles, and that you generated from like a pretty small recurrent neural network. And so you have this like sort of picture, right, of RNNs are able to learn a lot about syntax, even at modest sizes of the neural network and modest amounts of data. And I think that's sort of fascinating, and we don't have a lot of theoretical understanding yet of how they're able to do so. So today we're going to pick out a specific, let's say, functionality or skill that's necessary in order to understand language in general. So in particular, we'll look at stack-like behavior, pushing to and popping from a stack. So there's all kinds of reasons why you need to at least simulate stack-like behavior to understand language. But even if you don't sort of buy almost anything about syntax, you can at least probably buy this. When you see a subject, right, you're seeing the sentence they see, you want to push a subject until you see its verb, at which point you might imagine popping it. And then you see a new subject, they see that laws push laws. And the reason you need a stack is that you can now push another subject, right? So laws the lawmaker makes, you need to keep the word laws around, even though the sort of most recent subject now is lawmaker. And you can do this more, right? Laws the lawmaker makes in the reporter questions. And finally, at a long distance, you see the word are, which is the verb of laws. Now you can pop laws. And so, there's more like formal reasons why you need stacks in language, but hopefully this shows you that it's sort of important even from an intuitive standpoint. So to summarize, Rnns empirically seem to model language well, or syntax well, not all of language, but we lack theory that can help explain their success. Today we're going to focus on stacks. And so we want to have theory to help us facilitate the analysis of whether Rnns can learn syntax in general. And this work I see as sort of just a step in that direction. Okay, so I'm going to give an outline of the talk, and timing wise, just feel free to ask questions as they arise, as you feel compelled to. Don't feel necessary to wait to the end of the talk. So just feel free. So first, we're going to set the theoretical scene and summarize some of our contributions. We'll then go into some more detail, introduce a formal language that'll be sort of a formal object of study that reflects a core aspect of natural language syntax. We'll state somewhat informally our theoretical results. We'll explain some key proof ideas. So the proofs are pretty involved. And so we'll just kind of explain some of the high level, and then give some empirical hopes and sort of, let's say, an interesting first step of let's say, empirical work bearing out some of the theory, and then we'll conclude. Okay, so before I go on, any questions? Excellent. So today's talk is going to be primarily concerned with expressivity, which is sort of what can our models do? What can a function do? What can a class of functions do? So you have a model family like recurrent neural networks, which for the time being, I'll leave sort of not formally defined, so what can recurrent neural networks do? And this is usually framed through decision and recognition problems. This should sort of remind you of theoretical computer science kinds of things. You say you have a string of symbols, and you have to decide whether that string of symbols belongs to a language. So if you have some input, and maybe here's a language which is like any number of A's followed by the same number of B's, the decision model needs to decide whether the string is in the language. And now you have another input and the same language, and the decision here is no. So if an Rnn can do this for any string, make this decision correct, then it recognizes this language A to the n, B to the n. So, I mean, it's a little of a basic introduction, but expressivity is really what we're going to be concerned with here. So it's good to have sort of a simple definition or intuition. And so what we want to understand is, can recurrent neural networks recognize or decide languages that capture core aspects of human language syntax? And we're going to modify this question a little bit in the future to reflect more of what we actually do in NLP, but keep this in your head for now. There's sort of formal languages that reflect syntax, and how do they relate to recurrent neural networks? So there's been a lot of work, right, on understanding what kinds of functions Rnns can compute, what kinds of languages they can recognize. We're only one work in a long line of work. So we're going to give a couple of examples, but I want to emphasize that the theoretical setting that the proofs occur in decide a lot of what Rnns can do, and also decide sort of how reflective they are of NLP in practice. So one thing that you have to sort of decide on when you're asking questions about Rnn is, how many times am I going to allow the Rnn to sort of unroll over the input? So you have, say, once per token, right, where you'd like unroll the Rnn once for the word I, and then once for the word want, and then A, and then pizza, and then maybe make a decision. Or another sort of setting you could imagine, right, is that you read in the entire input, and then you sort of unroll as many times as you need before you've decided that your decision is done. Okay, so, I don't know if it needs saying, but the once per token sort of framework is effectively all we do in NLP, with maybe some caveats, but effectively we have this sort of once per token assumption, and that reflects what we actually do in NLP. The second sort of major component of the theoretical setting that matters is the precision. So this sounds like a sort of, oh, it probably doesn't matter kind of topic, but it's actually vitally important and reflects things about what we do in practice. So when you have a hidden vector, right, this is your hidden state of your Rnn, it's a bunch of rational valued numbers. How many bits are you using to represent those rational values? Do you have, say, 32 bits? Or 64 bits or 8 or something like that? Have you quantized it really low and now it's 4 bits or whatever? So that's one option for a theoretical setting. A popular option for a theoretical setting is actually log of n bits, where n is the sequence length, right? The intuition here is that without log of n, you can't even count the length of the sequence. So this allows you some more like wiggle room in your theoretical setting. And then sort of a third option is as many bits as you want, infinite bits, infinite precision. And this is, I mean, I'm going to argue not what we do, but it's a theoretical setting you can imagine. So with this sort of framework, let's go through a little bit of related work. I think the sort of fundamental work in understanding Rnn's computational power, and the one that most people are familiar with, if they're familiar with any of it, is Siegelman and Sontag, who proved that Rnns are Turing complete. And this is under the unbounded precision, unbounded running time scenario. So, it's like if you had the most expressive model of an Rnn you could possibly think of, they're actually equivalent to Turing machines. And so you can do whatever you want. So that's cool. That's a really interesting result. But it's really, I mean, not what we do in NLP. And so, there's been more work since then. One really interesting piece of work is from Gail Weiss, who showed with logarithmic precision and a running time that does what we do in NLP, right? Where you take a single token, apply a single recurrent update, and then sort of halt as soon as you've finished reading the input. There's this, interesting result that Rnns, say, can't count. They can't be arbitrary counting machines, but LSTMs can, because they can sort of increment in their cell state and decrement, and that's pretty interesting. So this is like a theoretical setting that's closer to, say, what we might care about in NLP. Like this might actually be learnable, say, compared to if you needed unbounded running time. There's just no way we would ever do that effectively. And then another result is on the same setting, and this is sort of concerning for us. It showed with logarithmic precision and this sort of once per token running time, Rnns and LSTMs can't recognize languages that require a stack. So it's like, oh, well, that's too bad. It's actually a really interesting result. And so it sort of leaves us scratching your head, like, what should we, so does that mean Rnns can't be doing sort of the right thing or understanding syntax in general if that really does require a stack? And this is where it gets really interesting to me, which is we actually change the setting again. So we study the finite precision setting. So now you've got some number of bits p, like 32 or 16, and that's it. You don't get more. And this changes the kinds of expressivity results you can think about in ways that I'll get into later. So now this is so we're changing the setting to be even more, we think, like the settings where people actually use Rnns in practice. So hopefully this brings theory closer to impacting what we do as practitioners. So, I don't usually work on sort of theoretical questions. I'm really interested in how they can bring insight. And so let's, in every way possible, try to bring our theoretical analysis closer to NLP practice. So an immediate result here, when you have finite precision, is that no model that has a finite dimensional vector memory, right, like some hidden state HT, or a stack of hidden states of its, whatever, a stacked Rnn or transformer or whatever, nothing can simulate a stack. And it's sort of for a trivial reason. I mean, it's modeling a stack requires unbounded memory. Stacks can be unboundedly large. That's sort of their like thing. And if your memory has dimensionality D, So you have, 1,000 hidden units, or maybe 1,000 times 8, whatever your GPT, and you have a bunch, but whatever. You have at most 2 to the d times p possible states if you have precision p, right? So every possible is just every possible configuration of your system. That's a finite number, so you can't handle stack in general. And so you're sort of stuck. So where do we go from here? The answer to me is actually changing the theoretical objects of study from the language side to actually reflect humans better. So humans don't use infinite size stacks when they're parsing and generating language. Theoretical models of human language have this sort of competence versus performance thing. And so you can imagine humans sort of being able to do these stack operations, but they really never, it's so hard to understand things that require deep stacks, they just don't do it. So we can ask questions about whether Rnns can handle bounded depth stacks. And so that's sort of contribution 1. Contribution 2 is a formal language that reflects things about syntax. It has hierarchical dependencies like human language syntax does, but it requires bounded memory, not unbounded memory. And thus it's possible that systems with a finite memory can actually do something with these languages. And then we prove a result that I think was very surprising to me, and I think is sort of fascinating. If you measure the number of hidden units, the dimensionality of your hidden state that you would need to generate or to process, and we'll get into that further, these languages that we've come up with, you actually need what you can prove to be optimally few, asymptotically, hidden units. So you're optimally efficient at generating these languages, and Rnns can do so by exactly simulating a bounded depth stack within their hidden state. And we show exactly how that's possible too. So we provide constructive proofs. Okay, questions here?
Hi, I have a question. So are we talking about just single layer of Rnn, or having multiple layers of Rnns changes their capacity, expressivity?
So we're talking about a single layer. And I actually, to keep equations from this talk as much as possible, I'm really not going to give you the full definition, but it's effectively just a single layer Rnn with like a single, softmax matrix giving you like probabilities of the next token, like a simple Rnn language model with one layer. So, okay. Yep. And then whether stacking multiple layers does increase the expressivity, I'm sure it does, but I haven't, maybe in a future paper we'll quantify exactly how. Cool, thanks for the question.
Sorry, John, we also have a question in chat.
Oh, sure.
Is this actually learned in practice, or is the proof just of representability? And Alex can elaborate on that. It's his question.
Sure, would you like to elaborate, or would you like me to answer now?
You can just answer, it's fine.
So at the very end of the talk, we will give some really interesting evidence, I think, that they learn something interesting. I highly doubt they learn exactly our construction, but we'll see that they learn something interesting, and sort of given exactly the number of hidden units that our theory predicts, they're able to learn something that I think you'll be interested in. But no, this is effectively a talk almost entirely on the question of expressivity, not learnability. Cool.
Can I also ask a question?
Yes.
Okay, so is your bounded depth related to mild context sensitivity from the linguistic perspective? So is that your boundedness?
It is not. So our languages are going to be regular languages. I don't know that much about mild context sensitivity, but our languages are not even context free. Does that answer your question or no? That does? Okay, cool. Great. So yeah, we'll get into why studying regular languages is interesting at all. That's sort of another aspect of why we think this topic is interesting. Right. Any other questions? Awesome. Okay. So we'll start with a language that is a frequent object of study when trying to understand whether a model, a function family, can handle syntax, and that's Dyck-K. Simply put, it's just Dyck-K is all strings of well-nested brackets of K types. So here's an example where I've sort of shown the hierarchical dependencies. You've got two types of brackets in this case, bracket type 1, bracket type 2, right? And so it's sort of like, you know, an interview question, right? It's like, how do you tell whether the strings are well nested? And you sort of do so by, well, you know, effectively implementing a stack, and you push an open bracket when you see it, and then you pop it when you see its closed bracket. And that's how you sort of remember which brackets should be opened and closed at any time. And this is a prototypical language of hierarchical structure in sort of a strong sense. So context-free languages, which I won't get into too much, think just like stack requiring languages, if you're not familiar, are frequently used to model human language syntax. They're not sufficient to model human language syntax, but they're a model of them. And there's a theorem that shows effectively that you can take Dyck-K and use it as sort of the backbone or the scaffolding of any context-free language. So it really, understanding Dyck-K is a lot, gets you a lot of the way to understanding syntax. And it really encapsulates the stack aspect of syntax in particular. So formally, we've got a vocabulary that's open brackets of K types, close brackets of any of K types. And if you like context-free grammars, it's generated by this context-free grammar here, where you always match brackets with the same type. And we'll connect this, actually, there's a little addition, we'll connect this to language modeling by adding an end of sequence token. Like in language modeling, probabilistic models, right? You like have an end of sequence token, so you know when to end. We're actually going to need that for our theory. So every string is going to be ended with some special omega that's not in the vocabulary. So that's Dyck-K. And it would be interesting to know if Rnns can generate or recognize Dyck-K. But we argue that it's actually not what we want to study. And if you take this example of an English fragment, laws, the lawmaker, the reporter questions, rights are, it's very hard to understand. And it's because of center embedding. So you've got laws are as sort of the outermost sort of sentence piece there. And then you have to sort of push laws, push lawmaker, push reporter. And it can be shown that, you know, even if you're trying to parse language, even if you're being very efficient, you need effectively center embedding depth amount of memory or amount of stack elements in order to parse this fragment. And so it's very hard to understand, and humans just don't generate these things in practice. Shallow fragments, though, shallow parts of language, like laws the lawmaker wrote along with the motion, blah, 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 can have long distance dependencies. And you actually can have deep nesting as long as it's not center embedded, as long as the memory that you need in order to process these things is a sort of a small amount. So you can say, you know, the person who went to the store and then to the car and then to the this, that you can do, but you don't say laws the lawmaker, the reporter, questions, rights are. So it's this memory bound that we think really makes Dyck-K not a very good object of study for syntax compared to the same language effectively, just with a bound on the memory, a bound on the stack depth that you can have at any time. And that's all we do. So we take Dyck-K and we say, now you can never have more than 4 open brackets that are waiting for their closed bracket. And so here, this is a sentence in Dyck 2, 4, because at this point, right, with this 2, bracket type 2, you have 4 things on the stack, but you never have more than 4. So it sort of has all of the stack-like pushing and popping of Dyck-K, you might imagine, but it is a finite memory language. So formally, you can define it in a couple of ways. One way to define it is to say, you know, at any time step, at any sequence element, you can count how many more open brackets there are than closed brackets. And that's sort of the depth in the language. So that's a time step t. And then you can just say, take all the strings in Dyck-K and throw out all the ones that ever have more than 4 that have more than m. In this case is the general stack depth bound, open brackets. Okay, so it's just putting a memory bound on Dyck K, and we'll add the special end of sequence symbol here as well. So the question we have, right, so we're talking about expressivity. We look at Dyck K, which is this sort of fundamental language of syntax, and then we say, well, what if there was a memory bound? We think that would reflect human language better. So now the expressivity question becomes, can Rnns recognize Dyck KM? And here's one more place where we're going to take usual theoretical work and try to just coerce it a bit more into being like what we do in practice. Take our theoretical setting and prove things in a setting that reflects more about NLP practice. So we don't train recognizers usually in NLP. We train a bunch of probabilistic models that conditionally or unconditionally generate stuff, generate labels, generate sequences, whatever. We don't have decision problems usually. And instead, we generate things. So you see a word like I, and then you maybe generate a probability distribution. If you're doing language modeling, this is exactly what you're doing. And you could imagine evaluating, whether the model only puts probability mass on the words that are like plausible continuations of this fragment. So, do this again for want, and then A, and then pizza, and then you have this end of sequence token, right? So we evaluate language models by perplexity, which is like a soft, version of this in expectation. But we really want to understand properties of recurrent neural networks as language models, not as recognizers. And so we're going to study this setting as language models. And just a quick intuition is we can evaluate something like, if I sampled from my language model distribution, would I only get grammatical things? And that's how you would know that the language model understands the formal language. Cool. And if you're wondering whether these two are actually different in theory, feel free to ask me. The answer is yes, but it takes a little while to get into.
Just to ask you a quick question though.
Yep.
So if you actually sampled from the probability distribution where you actually, your recognition capability was sigma star, which is to say that you don't actually have, well, I guess the question is, are you assuming a case where you can have zeros in your at your prediction level?
Yeah, that's a great question. So formally, we provide a definition called epsilon truncated support. Or locally epsilon truncated support. So locally, at every time step, you prove that there is some epsilon such that strings that are valid continuations get higher than epsilon probability, and strings that are not valid continuations get lower than epsilon probability. So you don't have to assume that. And then you can just make it as small as you want.
All right, so the probably in the paper, instead of saying if I sampled from this probability distribution, you'd say like with greater than epsilon support.
Yep.
The sentences being Dyck. Okay, cool.
Yeah, you would say after epsilon truncation, what I only get. We don't quite state it that way, but it's effectively that.
Okay.
Cool. And then it has to be it has to be locally truncated, right? Because if you truncate it, I mean, the probabilities of strings as they grow in length have to approach 0. So cool. Okay. Sorry, did that actually answer your question, John? Just to make sure.
Yep.
Cool. So yeah, the question becomes, can Rnns generate Dyck KM, not can they recognize it? And the answer is just immediately yes. They definitely can, and it's not even our work that shows it effectively. So Dyck KM, because it requires finite memory, it's a regular language. A regular language is any language that requires finite memory to recognize, and thus we can show to generate. If you're not familiar with these terms, don't worry about it too much, but regular languages have a machine, a finite automaton that has a certain number of states. And sort of you transition between the states, right? And it's finite in size. Here's an example for Dyck 2, 2. And sort of for Dyck KM, you can think about the states as all possible configurations of the stack of up to m things. And so the automaton for Dyck KM is k to the m states. And that's a lot. Think of k as your vocabulary size and m as your stack depth. So it's known that Rnns can simulate any deterministic finite automaton, and you need roughly as many hidden states as our hidden units. The dimensionality of your Rn needs to be about roughly the size of the number of states in the minimal finite automaton. So this sounds like, given prior work, you would need O of k to the m hidden units, and that's a lot. So it's like, yes, you could, but it doesn't mean anything because no one makes Rnns that big. So just to make that concrete, so previously known, you could use around O of k to the m. You could probably use O of k to the m over 2, but that doesn't help too much. That's the square root of that. So just thinking about this, giving it some concrete numbers, you've got maybe 100,000 words in your vocabulary, m is 3. So you need 10 to the 15 hidden units. And I know we love big language models, but no one is building language models that big yet, ever probably. So what we prove is that actually Rnns need at most O of m log k. And I'm giving you some constants here, 6 times m log k, because the constants are pretty small and actually make a very different prediction about how many hidden units you might need. So this is, exponentially better than what was known before, as log of what was known before. And then we actually also prove that not only is it sort of better than you might imagine, no machine that uses a vector memory could possibly use asymptotically fewer than m log k. So Rnns are optimal in terms of the number of hidden units they need to generate these bounded hierarchical languages. I think that's fascinating. Okay, actually, let me stop there for a second if there are any more questions.
Are you going to explain how?
I'm going to explain some key ideas how, yep. Okay, key proof ideas. I'm sorry, go ahead.
Sorry, and we also had another question in chat from Keith. As a test of this bounded memory, what is the size of stacks in sample text, for example, books? Do we see the largest bounds increase with the size of the corpus, or is the stack always bounded?
It's a great question. So there's a paper that I cite in our EMNLP paper that effectively finds that if you are really wanting almost all the distribution, m should be 3. And if you want like literally every sample, m is no greater than 4 or 5. I can't remember the exact number, but it's quite small. Yeah, so we're interested in general m in part for things like Rnns have been shown to handle XML that has, deeper but still bounded depths. But empirically in language, I mean, you saw the example of m equals 3 that I provided, and it doesn't happen much. So m equals 3 is a great approximation. 4 and 5 are sort of getting really into the tails. So as the corpus grows, I would probably bet money that you don't get beyond 5, but it's a great question. Okay. So let's go through some key proof ideas. There's always more details if you want it, and our appendix is something like 20 pages long. So there's always more details, but I want to give people some key intuitions at the very least. So our proof shows that this result is possible because Rnns can exactly simulate a bounded stack. So somehow we need to first figure out what the memory is going to look like before we see how we're going to operate on it. So Rnns have a vector memory called HT. And for now, we can think of HT as having dimensionality k times m. So that's not what we said before, but for sort of pedagogical purposes, k times m. And we're going to conceptually split it into m stack slots, each of dimensionality k. So you just say like the first k or the first slot, second k, and we call them stack slots because each one of them is going to optionally encode something on the stack. So maybe the top of the stack is stored at the first stack slot, for example. And so this is good. This is a way to represent a stack of vector values. This is effectively just concatenating them all. And we're going to encode for now each of the k types of open brackets that we need to store on our stack memory as a one-hot vector. That's why they need to be dimension k, right? So bracket 1 gets the one hot vector at 1, then 2. Right, and so now, and you can also just sort of read out which bracket is encoded very easily because it's a one-hot vector. So how would you simulate the actual pushing and popping? How would you apply this in an Rnn? Well, it would be nice. It'd be nice if you could push, apply a push operation like this. So you got some stack slots. Here's slot 1, 2, and 3, and then the fourth one is empty. You want to push, so you shift everything down. You shift the first slot into slot 2, etc. And and then you can write to the top slot because now it's empty, it's free. And you can do this. You can do this with an off-diagonal matrix. So these I's are identity block matrices. So you sort of, it's like the identity matrix but shifted down by k dimensions. And if you in your head you do this matrix multiplication, you'll see that slot 1 gets written here, nothing gets written here, etc. So that's nice. But we also need to pop, and it'd be nice if we could pop to the vector stack like this, where you shift everything back up, right? It's the natural sort of operation, and so when you shift up, whatever was in the first slot is sort of poof, vanished, erased, because there's nowhere for it to be stored. And you can do this as well, right? So now it's again just like the identity matrix, but now you sort of like pushed it up by k dimensions, and it does exactly what you want it to do. Pretty simple, pretty cool. It's kind of this symbolic-ish operation. But the problem is that if you recall the recurrent neural network equations, there's only one W matrix. There's only one multiplicative matrix that actually applies to the old memory ht-1, right? So you could have W push, you could have W pop, but you can't do both. And if you summed them or something, that wouldn't work. So this solution can't be applied as is, simply because you have one recurrent matrix. And there's an extended model of Rnns actually, in which this is perfectly possible, called second order Rnns, but that's not what we use in NLP. So, so let's keep that equation right there. And we'll show how we actually do this in the sort of simple Rnn. And when I say simple Rnn, I sort of just mean this usual equation for an Rnn. We're going to keep 2 copies of the stack. So we're sacrificing some memory efficiency to get it to work. And we're going to keep 1 copy empty. So that means the 0 vector in this case. So this is empty, it's the 0 vector. This copy represents the stack. And we're always going to read from both copies. So I've got 2 of my push matrices here that I'm going to apply. And so because I've got both of them, each of them is going to try to, one of them is going to try to read from the first one of them is going to try to read from the other one. And so now I can read from either copy of my stack. And I'm also always going to write to both. So I'm going to do what's needed to be done for a push and what's needed to be done for a pop, both, every time step, right? So now here's what the hidden state would look like if I pushed without writing a new element yet. Here's what it would look like if I popped. Okay, and so now the problem is that we've broken our guarantee that 1 is always kept empty, and this is easy to solve. So now you've got your sort of 2 copies of the stack. You need one of them to be empty. Well, the one that should be empty corresponds to the element or the copy that corresponds to the operation that didn't actually happen. So let's say the input says pop, right? It's like a closed bracket. In this case, think about beta here as a very large number. If I just say that all of my closed bracket pop operations are going to add a very large number. So you see in our recurrent equation, you've got uxt here. Uxt can add a very large negative number to just the copy of the stack corresponding to the operation that didn't happen. And now I've got something here that adds zeros to everything else. So now I've got this S2, S3 pop stack, and I've got some very large negative numbers here. All of them are less than or equal to beta, a negative beta. And so if I scale these up to be very large by scaling the weights to be large, so very large and negative here, and then very large and positive here, this becomes S2 and S3 again, because I've scaled them and then applied sigmoid to squash back to 1, or to the 1-hot vectors. And then because these were all very largely negative, they become 0, and so that's empty. And so for this simple Rnn, that's effectively the entire stack construction. You do both operations, and then you zero out the one that didn't happen. Okay, any questions there? Cool, so it's actually quite, I mean, you know, it's not a terribly complex operation, but we were wondering if you could do better with LSTMs. You know, obviously the gates of the LSTM were introduced in order to try to solve the vanishing gradient problem, but you know, they also might kind of provide modeling capacity themselves. There's been some work that sort of suggests that, and so we're really curious, like, do you get any benefit from that? And you can effectively cut the hidden state size in half by not needing 2 copies of the stack. And what's more is that it actually only uses the gates of the LSTM. So I won't go too much into this construction in this talk because it's quite involved, but I'll give some high-level intuition. So again, they're going to just use their gates. So we'll talk about sort of what each gate does, and only look at the diagram there if you're really interested. But semantically, the input gate you can think of as helping determine where to push a bracket. So instead of trying to write a bracket to slot 1, I'm always going to try to write a bracket to every possible slot. Then the input gate will actually determine where to write the new bracket. So that's going to say, where should I push to? Where to input to? It's kind of nice. The forget gate will actually help determine where to pop a bracket. So a forget gate in an LSTM allows you to zero out vectors in the cell state, or zero out values in the cell state. And that will actually implement the popping motion by cleverly detecting where the top of the stack is and setting the forget gate to 0 exactly where it needs to be. And then also interesting, the construction actually only has the top of the stack in the hidden state. If you recall, and we're not going to get into too much detail, but the LSTM has a cell state and a hidden state. And in our construction, only the top of the stack actually goes into the hidden state. So the output gate outputs just the value at the top of the stack. So it's really easy to read out from the vector memory where the top of the stack is without seeing any of the elements beneath it. And so these 3 gates together, we show, can also exactly simulate a bounded depth stack just by themselves. I think that's pretty fascinating, with no other dependence on the history at all. So the last key idea, which I'm again mainly going to gloss over, but hopefully give some intuition about, is moving from an O of mk solution, which you would get if you used our stack construction, and you have to prove stuff about the probability distribution. That's all actually very technical. I'm not going to get into it in this talk, but even if you did all that, you would still have an O of mk solution. We claimed we had an O of m times log k solution, which is considerably different. And this just means that the stack slot needs to be much more efficient. And we said that each of the k brackets was encoded by a 1-hot vector. Well, if you need to go from k to log k, you know, idea number 1 is just, instead of a 1-hot vector, use a distributed encoding where you assign each of the k brackets a bit string of length log k. You've got 2 to the log k bit strings for that length. And so now bracket 45 could be encoded like this. And there's a couple of things that go wrong here. Making the stack construction still work is not obvious for the LSTMs, at least. For the Rnns, it's pretty easy. But now it also becomes hard to figure out which bracket is encoded at the top of the stack. Again, if you have like a simple readout function. Yeah, so the solution that we use actually uses a constant factor more space to allow for sort of easy reading out of the brackets, and I'll provide you more details with that really only if you're interested. And so that's why you get the constants that you get. You sort of have extra amount of space to allow for you to read out the identity of the bracket. And that's effectively all of the sort of insight that I'm giving into the proofs for this talk. The last thing I want to talk about is a couple of experiments that I think point to some really interesting behavior. So we ran we ran some experiments in learning to generate Dyck KM. So to start, in prior work, if you tried to train an RNN, or really train anything that doesn't have unbounded memory to recognize Dyck K, it sort of has been shown to just not work which under our theory is a foregone conclusion, because if you have finite memory, you just can't do this. But we find that DyKM is actually learnable. So we train, again, LSTMs as language models here. So we like define a distribution over DyKM, and then we sample from it and train LSTM language models on those samples, and then evaluate whether the probability distributions learned by the LSTM sort of like obey all the checks of understanding sort of which brackets can be closed when. And so looking at this plot here, I want you to focus on the red values, the red plot lines here. So we've plotted the performance. The actual metric isn't too important. It's effectively what percentage of the time stratified across bracket distances, what percentage of the time does the model know which bracket should be closed? It's an evaluation of the memory of the model. So if it always knows which bracket should be closed next, it's sort of managed its hierarchical memory properly. So a value of 1 here, you'll have to trust me if unless you read the paper, is a really convincing metric that it totally sort of understands how to manage its memory. So the dotted lines are in domain on a development set of a given length, and then the solid lines are extrapolation to longer lengths, up to 2 times, I think, longer than strings seen at training time. But remember, you never go deeper than the stack depth. So here's m equals 3 for this top plot, and then m equals 5 is the stack depth for the bottom plot. And so the red line is what I want you to focus on for the following reason. We have different values of k here. And for small values of k, like 2, when you've seen a number of training tokens, so here's 10 to the 4 up through 10 to the 7 training tokens. For small values of k, you end up seeing every possible configuration of the stack at training time. So all you need to do is recognize sort of which strings go into which states, and you can just simulate sort of the finite automaton that you saw evidence for at training time. But at k equal to 128, you actually see a fraction of a percent of the possible stack states at training time. So there's so many stack states. There's 128 to the 5 possible configurations of a stack, when each of the things can take on one of 128 elements, and you've got a maximum stack depth of 5. So even when you have 10 to the 7 tokens, you've seen a vanishingly small percent of the stack states at training time, and yet in an extrapolative setting, you're able to perfectly close these brackets, definitely seeing, and we calculate the exact number, but seeing stack configurations at test time that you never saw anything close to at training time. So this is really something that looks a lot like stack-like behavior. And I think that's pretty fascinating. So not, again, the focus sort of the work, but just to give sort of a bite or a little bit of empirical hope. And one last thing here is that we actually set the hidden dimensionalities of our LSTMs to the dimensionality for each of these values of k and m that our theory predicted would work, and just sort of did that, and it works, and that's pretty cool. So some takeaways here, some thoughts. Our work sort of finds itself in a discussion relating to the Chomsky hierarchy, which might have come to your mind if you're familiar with it. You've got sort of Turing machines at the top of the Chomsky hierarchy of kind of complexity of languages and machines that recognize those languages. And you've got sort of intermediate steps, context sensitive, context free languages, sort of at the bottom, at the least interesting part of the hierarchy that sort of can't describe things about human language. You've got regular languages. And the problem with regular languages is that any language that requires finite memory is regular. We argued in this work that actually you should study finite memory languages exactly because in a realistic setting, that's all our Rnns, that's all our transformers, well, some transformers can recognize. If you have a finite memory, if you have a finite vector memory, all you can do are regular languages. So we need finer grained theoretical tools. And we showed that memory efficiency can be a tool like that, allowing you to make claims about sort of how many hidden units you would need, allows you to understand and to look at the mechanisms that are actually possible for these systems to learn. And hopefully that will give us some insight. So not only do we give some much more detailed descriptions of our constructive proofs, we actually also provide PyTorch implementations. Hopefully this will allow people who are interested in analyzing sort of similarity between representations and stuff to sort of just plug it into PyTorch and start doing some interesting empirical analyses. So yeah, we've also got implementations of the experiments up. Happy to take questions and hoping that this has convinced you that, for one, Rnns are, say, better than I would have expected at handling bounded depth hierarchy, and two, we can really work to build theoretical tools that analyze the relationship between neural models and languages in ways that sort of become closer and closer to how we use these models in practice. Thank you.
Thank you so much, John. And I'm just looking at the chat. Okay, we don't have any questions there. And so if there are any questions, we can take them now.
Could you say a word about the little o part? So I buy your big O, but I just wanted to know how you know that nothing smaller can handle these languages.
Awesome point. So the argument is actually pretty nice. So I said that we had k to the m possible stack configurations, right? So you have a finite automaton that has k to the m stack configurations. What that effectively means is there are k to the m strings that need to be assigned different representations under any model, independent of computational power, that wants to recognize or generate this language, right? And it's like saying that if you want to, implement a stack that can have k things, m things of k types, every possible stack configuration needs to be assigned a different state in your machine. Does that make sense so far?
I think so.
Right, so if you had two stack states that were assigned exactly the same representation, you're toast, because as soon as you have a continuation of a string that distinguishes those stack states, say by having a different type of close bracket, you started from the same representation. So this is like a communication complexity argument. So imagine, for example, you have a string that's just, you have k to the m strings, all that are length m, and it's just all possible strings of length m. And you've got k to the m of them, and they're all different, and they're all open brackets, say. So just k to the m strings of m open brackets. Each one is different, right? Because that's the number of configurations of open brackets you need. And each one of them has some suffix that only closes that string and none of the others, right? And it's just like the sequence of m close brackets of the same types in the opposite order. So if you wanted to open, say, whatever, m brackets of some configuration, you need to close those m.
Right.
So you need
palindrome, essentially. Yeah.
Exactly. So in order to separate these, you need, any machine needs to assign each of these strings different representations. And if you have 2 to the d times p configurations of your vector, right, because you had dimensionality d and precision p, then you just say k to the m is less than or equal to 2 to the dp. And then you get, that d is equal to m log k, or it's greater than or equal to m log k over p, and the precision is O of 1.
But could you not, I guess I'm wondering if there's a more efficient lossless compression, thus, which would give you a smaller number of states fundamentally. Maybe it also has to do with, did you define the nonlinearity to be limited in some way?
No, so if you had a Turing machine deciding how to update the state at every time step and taking infinite computation time to do so, you still couldn't do this, right? So actually the proof doesn't rely on finite automata at all. It's just making the argument about the palindromes allows you to prove it for any function. So not even just Rnns, just any possible function. Couldn't possibly do better than m log k, O of m log k. You get, yeah.
John, is your question answered?
Yeah, that's a great question. Is it answered?
Well, I'm in the first kind of RNN, so I'm going to infinitely compute for a while until so you can go on to something else.
Of course. Yeah. So I think it's so we give a proof in the paper, and it ends up being pretty short because of this proof by contradiction. Effectively, if your machine assigned two of these palindrome strings the same representation halfway through, then it would get something wrong later on, independent of how hard it tried to figure it out. It's like it just doesn't have enough possible ways to represent different things. But also happy to talk about it more later as well.
Okay.
Also, I think Khalil has a question.
Thank you so much. This was really, really nice. So I have a question related to the question I asked earlier. So I definitely agree with you about the finiteness of center embedding. However, there are potentially other kinds of dependencies in natural language, and some of them could be also highly finite, 2, 3, 4, however crossed. So the most famous examples that I've never liked, but these are like Swiss German, where you get 3 crossed. It's just 3. Now, could one use like multiple hidden layers in the RNN, or does that completely destroy your enormous exponential reduction in the number of hidden states?
That's a great question, and it depends on whether there's interaction between, or let me be more precise, it may depend on whether there's interaction between the two sort of types of dependencies, right? If for example, like if you were to take this language and just say, there are 2 different hierarchical sort of things going on, and I can sort of intersperse the tokens whoever I want, right? Like you have one nicely nested string of some types of tokens, and then you have a different nicely nested string of other types of tokens, and they don't interact, they're just sort of the tokens are interleaved, then the construction you can just have 2 independent stacks that are always pushing and popping whoever they want, that don't interact with each other at all. And so the construction does fine. It scales exactly how you would want it to. I haven't proved that, but I'm confident in it. It's like if you wanted, to just like implement 2 stacks in the RNN and have them not talk to each other, that's fine. If there are, and I'm sure there are, dependencies between how things can push and pop, I'm not sure, right? Maybe the effective stack depth becomes larger if you were to try to do it. Maybe you could do the 2 stack thing. I don't know enough about these sort of crossing dependencies to make a solid claim, but if you showed me a formal language that was simple enough that had this kind of behavior, I would love to chew on it a bit. But that's the best answer I've got for now.
Thanks. If I could just add, like a multiple context-free grammar could generate such things, and you could think about how you, except it's at least context-free, so you, but that would be the kind of language, that would be the kind of grammar you would need.
Yeah, I think that's a fascinating question, and I don't think I've thought about it enough to give a more precise answer, but I'd love to think about it more.
Do we have any other questions?
I'll ask a question. Can you hear me?
Yes, go ahead.
Cool, yeah. So I really like this notion of, looking at sort of like complexity or memory instead of just like recognition capacity. And I'm wondering like how generalizable you think this is to other architectures, like particularly transformers, because it seems like your analysis makes a lot of sense in this regressive setting, but you could also imagine applying it to like, a transformer encoding a sequence. And I'm wondering if you thought about that at all.
Yeah, I think with decoder only transformers, so transformer language models, GPT, etc., it directly, you don't have to change anything. If you meant by encoding a sequence, like an encoder decoder model, there you could argue something about the distributions expressible by the decoder. Sorry, you're referring to the fact that you're arguing about dimensionality size, or about the generation versus recognition. I actually spaced there for a second. Which
Oh,
question?
sorry. Yeah. So I was just thinking about, you know, like how much space you need to represent finite languages,
sure.
but applying that to transformers, and thinking about like how self-attention behaves there and whether you can prove anything similar.
Yeah, I think you can. I mean, at the very least, you can look at sort of the like the dimensionality of all the things you can be reading from, and or like say take the dimensionality of probably it's the same across all layers of a given layer, and then make arguments with respect to that. Say d is equal to, and obviously you can read over many past states, but you could still make a statement with respect to either the individual layer dimensionality or say 512 times that dimensionality, for example. If you had some fixed context model. I think the issue with transformers is actually more in figuring out what class of languages they can do anything with. Like there's a lot of regular languages, right, that they can't recognize, and they definitely can't recognize, or at least decoder only transformers can't recognize even like one or something like that. Michael Hahn had a paper on that. So I think that the memory thing scales, you have to make an argument as to like what you want your unit or size of memory to be. But yeah, I think that it's like, I haven't worked everything out, but I'm confident that it's a good direction there as well. I'm just not totally sure how. So, but if you want to work on it, yeah, I'd be happy to talk more about it.
Yeah, cool. Yeah, maybe we could talk offline. Thanks.
Thank you.
Do we have any other questions from the audience? Okay, I think in that case, we can all thank John for this great talk. I'm sure for many of us, this is not the usual talk that we get, so it's really good to have that once in a while. So it's a nice change. Thank you so much. And I think we can give John a break before the one-on-one meetings can start.